Idea is basically to develop this kind of hardware system right now. But in this PPT, I'll just give you a analysis on the topic that what are the base requirements and what things you need to understand the basics behind the topic, and then we'll move forward to the hardware design. And with the help of some modules that I have with me, I'll be showing you the connections, and we'll be joining multiple sensors together, and from there we'll be sending data to the cloud platform one by one. So before we start further, we need to have a outline of the domain of interest right now, that is air pollution. And before we start working on the topic, you need to know the severity level of this particular, uh, we can call a silent killer, the air pollution. And if we check the World Health Organization reports, it is said that almost 7 million deaths are reported every year just because of repeated exposure to indoor and outdoor air pollution. And this further leads to some prime health issues, including stroke, heart disease, lung cancer, and variety of respiratory health issues, including we can say your nervous system issues also. They are all considered within this air pollution area. And while exploring this particular problem that we have across the world, you can observe from this slide right now that our zone is widely targeted, and among all these, India is the most targeted area where air pollution instances are increasing day by day, whether we call it just because of increase of industrial activities over the years, or it can be due to the traffic that is increasing definitely with every passing year, and plenty of changes in our lifestyle that is also contributing somewhere to the air pollution instances. So this basically shows that the South East Asian region, especially India, is highly targeted by such type of crises. And definitely, we as a researcher, we as an engineering experts need to take some relevant actions in this domain to deal with the challenges that our next generations are expected to face. So after checking the outline of this particular area, since I told you that this air pollution instances, they may occur with the outdoor areas as well as with the indoor areas, I'm more focused here about the indoor air pollution. You may observe that over the years, if you check the literature that was published like 5 or 10 years ago, there was more potential towards outdoor air pollution. Very less researchers were considered about the indoor air pollution instances, because at that time influence of the outdoor air and the work techniques, work culture at that time was more influenced towards the outdoor areas. But as time is changing, we are taking up work from home jobs, and the majority of us spend like 80 to 90% of our routine time indoors, especially kids or mothers and even elderly people. We spend more of our time indoors. And this goes with the people who are doing office jobs. They are also sitting entire day, they are sitting within the buildings. So this is the high time to judge the level of indoor pollution we are getting exposed to every day whenever we are sitting within the closed spaces. Although we believe that we are sitting within the room and there are no particles from the outside in our observation, so maybe we are safe. But the strange fact is that even within a home or even within a residential or commercial building, there are still unlimited sources of pollutants. From this particular image itself, you can see that almost every part of your home is affected by certain kind of pollutants. Whether we talk about the kitchen area, that is definitely more exposed due to the routine cooking or heating instances that takes place. Similarly, the bathroom areas, they are also affected by different kinds of mold spores, humidity or sprays, etc., that we may use. Garage areas are also affected by plenty of gases or solvents, pesticides, etc. Similarly, the bedroom, basement, and even the living room and home office, etc., all these parts are highly affected, including your attic region. So this shows a very long list of pollutants that keep on affecting our lifestyle. Now, when we are narrowing down a research study, I'm showing all this aspect to you, considering that if you are working on a project, if you are working on a research study, how you narrow down your aspects to lead a specific outcome out of that. So we started with the wider domain, that was air pollution, and it was affecting, the stats show that it is affecting almost every region in the world. Then we focused to the target area, that was your indoor air pollution, and we just tried to judge that what are the definite pollutants that may affect our lifestyle within the building areas. Now, moving further, when we are talking about development of air pollution management system or a monitoring system by using some sensor network based on Internet of Things. So it usually requires you to start from the very essential pollutants that you can cover up within the limited range of sensors over there. Because in order to monitor all these elements that are listed on your screen right now, you need a very huge sensor network. So instead of working on a very huge sensor network right from the beginning, you can start from some basic pollutants first, and then you can expand your network further to cover up more number of pollutants. So here we further segregated these components, because this case study was also a part of my PhD project few years back. So from there we did a step-by-step analysis on that. And then after analyzing the local regions or the rural areas that were more of a focus for our case study, we started segregating the most essential pollutants that are affecting human life in those areas. And for that, what we did is we selected the most relevant pollutants by taking advice from the Pollution Control Board experts, as well as from the research studies that were published from those areas. And for this, we included some regions of Chandigarh, Punjab, and Haryana, as well as Himachal. So these four states and a limited set of sites from each one of these states, we started observing, and we took a decision about the most relevant pollutants from there. And after observing all these, we further started looking forward for the relevant hardware that could be combined somehow, that could be joined into a IoT system, and we can take measurements from the real-time environment. And for this further, we segregated our installation sites as well as the focus parameters into these specific number of observants. And during this case study, we have implemented the sensors in these 5-6 different areas that included definitely all four states that I have discussed. And then the focus parameters for us that we decided included PM10, PM2.5. They are basically your dust parameters. And then there were 4 gas parameters, including VOCs, that is your volatile organic compounds. And then we had 2 thermal comfort parameters, because they play an important role in deciding the comfort level of human beings that are staying within the a room or a building. So these became the most relevant parameters for the case study further. And then we made a decision about the relevant hardware that we could join up for this monitoring, for a real-time monitoring of all these parameters on the relevant sites. And for this, basically, you will find like thousands of different sensors are already available in the market that you can pick up to design these kind of hardware system. So we worked on a huge analysis on what are different hardwares, what are their pros and cons. And for that, we have even published a book where all the selection criterias we have mentioned, that how you can choose a specific hardware for conducting a case study. We even published some detailed literature surveys on the hardware design decision making that were published in some reputed journals, so that the same problems that we have faced during selection of every element during this design process, we could guide it further for the upcoming researchers. So if any one of you are also planning to conduct such type of case studies, you can find plenty of references for this, and books also we have published for this. So currently we are focusing on the type of hardware that we decided to use for setting up this case study. And it included the very first thing, Arduino Uno. That was your main microcontroller. We have discussed about it yesterday as well. Similarly, we moved forward to a Wi-Fi gateway in this case. That was more relevant to our requirement at that time. So we started with ESP8266 module. This one also I have shown you yesterday. Then further, for temperature and humidity measurement, we picked up one basic sensor considering the recommendations from the literature. It included DHT11 sensor. Definitely, you need to check the specifications of the sensors, and you need to ensure that sites wherever you are monitoring that falls within the measurement range of this particular sensor. So accordingly, the decision was made. And then this SDS011 sensor we decided for measurement of dust particles that include PM10 and PM2.5. Furthermore, we had CCS811 sensor that can measure two parameters, including CO2 and VOC. Similarly, here we could measure PM10 and PM2.5. If anyone is not aware that how this 10 or 2.5 is indicated over here, this is basically the size of particle in microns. So when we call it like PM 2.5, it means a dust particle with size less than 2.5 micron. And when it is 10, then a dust particle with size less than 10 microns. There are many different ranges of dust particles that are present in the surrounding environment, and accordingly the analysis are conducted. Then comes a multi-gas sensor. Although this gas sensor is capable enough to measure 6 to 8 different gases, but we have used it to measure specifically CO and NO2. These two were our focus areas. So we preferred measuring these two based on the elements that we have decided initially. So these hardwares we have combined, and for this these are the sensor specifications, that the prices etc everything is listed based on the time when we have conducted this case study. Currently many of these sensors have become more expensive, few of them have become less expensive, so accordingly the market changes you may see for this. So for this, you can observe these are the measurement parameters, and the typical ranges of all the sensors are also mentioned over there, so that we can pick up the right element based on the field requirement only. So this is how the hardware-based studies we take up, and then we start a decision about their deployment by considering all the relevant parameters. Along with this, the things that are listed here, along with this, you will find one more important thing that we call operating range. Operating range of sensors, which is currently not mentioned over here. There are two things. One is measurement range, other is operating range. Always remember this whenever you try to buy a hardware sensor unit for any of your project. Operating range is this. This is the range for the specific parameter that your sensor can measure. Here also, for each one of the parameters, I have listed the operating range, sorry, the measurement range. The second thing is operating range, which means the thermal conditions or the temperature and humidity variations that this sensor can accept in the field environment. Some sensors are designed to operate maybe within 10 degree to 50 degree Celsius temperature only. If you place them in other than that, they may malfunction, they may fluctuate, the readings may be wrong. So these can be different options over there. And accordingly, you may have to pick your hardware considering the site specifications. So all these things come into play when you make decision about any sensor. So Arduino Uno basics we have studied yesterday, so I'll not be repeating this again. Rather, we'll be doing this on the hardware side after this. The sensor, this one, DHT11 sensor. A little bit of introduction about this I have given you yesterday. This sensor I have shown you in the hardware. It consists of 3 pins that include one VCC, one you will have is ground, and third one you have is a data pin. These 3 pins you will find. And accordingly, you make connection on the Arduino side as well. It includes like this one is your, for example, a data pin. Similarly, we have a 5 volt and a ground. 3 pins you may need to connect on the hardware side. Next, we have SDS011 sensor. This particular sensor can measure, as I told you, two things. We are using it right now for measuring PM 2.5 and PM 10, two things that we have listed over here. So for these, we have these number of pins available, but not all of them you need to connect. Rather, we have mainly the connection over a 5 volt, then we have one ground, then we have one TXD pin, and then we have one RXD pin. These are the lists that we need to connect. So similarly, now 5 volt and ground, every one of you might be already aware of. Yesterday also we have discussed it. 5 volt, you connect with the 5 volt of your microcontroller, down with the ground of your microcontroller. For the TXT and RXT, we need to be very careful. Those who are going to do it for the first time, they need to understand that TXT and RXT lines are always required to be connected in opposite connection. Means if a TXT you are taking from one terminal, it will be connected on the RXT on other side, and vice versa, because that will complete your transmission channel. The sequence of communication accordingly you will be following. So starting from the transmission to the receiver, like this is your transmission pin, and this is connected on the receiver pin over here, the second one. And then last one here, green one, is your receiver pin, and the first one here is a TXD. So accordingly it is connected. Whenever you have a sensor that works on TXT and RXT, this is the same technique you follow, the opposite connection, so that the communication line can be completed. Because if one transmits, then only other receives, and same goes for the other side. The acknowledgements will be received from with one transmitter and the other receiver accordingly. Moving further, we have a CCS 811 sensor that we discussed, that we have used it for measuring CO2 and VOC components. And inside this also, the sensor contains multiple pins, but not all of them we need to connect. Instead, we need these 4 pins only for the initial connections that we have. That includes your SCL, SDA, 3.3 volt, and ground. These are your simple pins we need, and the connection accordingly we can make on the Arduino side. Note that this particular sensor works on 3.3 volt. So accordingly, on your sensor and on your Arduino, you have to match a 3.3 volt connection that you will find right beside your 5 volt pin. So accordingly, the connections we have to make. And similarly, for this SDA and SCL pin, if you remember the discussion that we did yesterday, I told you that we have dedicated SDA and SCL pins right here by the end of your digital port. The last one is always SCL. The second last is always SDA. So data line and clock line you will find like this. And if you don't want to use them from here, the second option is on the analog channel as well. On A4, you will have SDA. On A5, you will have SCL. So these are the two options you will find for the connectivity. Either you can use this one or you can use this one. Both are good. Any of these you can choose. So for a quick response in the chat box, if you remember the interfaces that we have discussed yesterday, about sensor interfaces we have discussed, if anyone can quickly update in the chat box what kind of interface this sensor is following. If you remember what interfaces I have discussed yesterday, the specifications I have told you. Just by looking at the names from here, you can identify which interface you are following. If anyone can update in the chat box quickly that which interface this particular sensor is following. I'll wait for responses in the chat box quickly. If anyone doesn't remember or need me to tell you, then also you can put in the chat box. We are all here to discuss, share, and learn definitely. Anyone in the chat box? Great. So I got to one response, I2C interface, definitely. Other than this, we have discussed about 2 more interfaces. So if I just go back and we talk about this interface, anyone remembers what interface this one is with TXT and RXT line? Yes, UART based interface where we have the communication through TXT and RXT. Very good. So at least we are able to connect with whatever we have learned yesterday, and proceeding that we are making the connections over here. So moving forward, the next one we have is a MISC sensor. This is like a multi-gas sensor, we can also call it. And this one you will find from many different vendors with different capabilities. Some of them are able to measure 2, 3 different gases. Some of them can measure even 8, 10 gases. So accordingly, the connections you can make. So here we have this particular sensor that consists of the dedicated pins for these 3 gases, and other than this, with the software coding, you can measure remaining 4, 5 gases as well. There are some dedicated functions to measure other gases also in the software itself, and the remaining connections will be making with 5 volt and ground itself. So in our case, we were using it for only 2 these target gases to measure, NO2 and CO, and accordingly we did that. And here the connection you can observe is with A1 pin and A2 pin. So for instance, this one I have A1 and A2 pin. So if anyone can just quickly let me know what type of sensor it is. I have discussed this also yesterday. When we connect sensor on digital or analog pins, what we call them in simple terminologies. If anyone can quickly put in the chat box what type of sensor it is. Anyone? Okay. Or in simple terms, we are calling it a analog sensor. This is an analog sensor basically, and it is going to measure a gas. So yesterday we discussed about analog and digital sensors. Analog sensors that can communicate over the analog channel of your microcontroller, and digital sensors that can communicate over the digital channel with signal 0 and 1. So this gives a continuous range of value, and if a sensor gives 0 and 1, that is by default we call it a digital type sensor. Okay, so moving forward, other than this, for the Wi-Fi, we have used this particular module that I have shown you this yesterday as well. As I told you yesterday, that on this module we have 8 different pins, but not all of them are connected during the hardware connections. Instead, we use some dedicated pins out of that. Note that again, this works on transmit and receive lines. So accordingly, you may have to choose them from your Arduino. Like here we have transmit and receive pins, so we can connect them alternatively over here. Similarly, the ground, of course, you have to use on the dedicated ground terminal. This 3.3 volt you have to use on the 3.3 of your Arduino. And then one more pin that you need to connect is this enable pin, and this is also connected on the same potential as that of your VCC, that is your 3.3 volt. So these both will go to 3.3 volt. Others, we already know where they are going to be connected. Remaining these 3 pins, they are not used for setting up a Wi-Fi connection, or to setting up a gateway with ESP8266. So accordingly, we can just keep them not connected. So this circuit again will be following while setting up your hardware and software for the system. Ultimately, we combine all these hardware units together to set up your hardware monitoring system design. That includes in the center your microcontroller. Then we have the thermal comfort sensor. Then we have the dust sensor. We have 2 gas sensors. And I have taken help from a breadboard to complete these connections. Reason being, we have limited 5 volt. We have limited 3.3 volt connection. We have limited ground connection available on your Arduino, but we need to connect multiple sensors. So we can make extensions on the breadboard directly. Like I have shown you a simple example over here. One side I dedicated to 5 volt, and other side maybe we can use for 3.3 volt, and one more side we can use for the ground. This is just a generalized diagram. Although we use it based on the specification of a breadboard. So accordingly, we dedicate pins, and then we can use extensions from there to complete your hardware design. So this is just a quick idea about how a case study is designed, and how we proceed with the selection of different hardwares, and then how we combine all the setups into a sensor network by using all the individual hardware units. Now, in order to make this work, this particular hardware arrangement, in order to make it work, we definitely need a software code that we can design by using Arduino IDE platform. So that we'll be discussing further. So I'll stop this presentation over here, and now we will move to the software part of the study. And in this, I'll be opening one existing code, because we have limited time in this particular session. So I'll not be designing the software from the scratch over here. Instead, I'll be using the already designed software unit, and that I'll be explaining one by one to all of you. And I'll also explain you how we use different set of sensors from the scratch on a Arduino platform. So every part we'll be discussing one by one. Don't worry about that. But instead of writing the entire code from the scratch, I'll be using one pre-designed code. I'll explain every part of it, and then we will be setting up the hardware. I'll turn on camera for the hardware, and one by one we'll make all connections, and then we will visualize results on the screen again. So starting with the first set over here, we had 4 sensors. And as a beginner, when you are building up a software for this, you will always get some help from the Arduino IDE platform itself. I told you yesterday that you will always find some examples on the file section of your software, and in that section you can easily access your different types of sensor libraries, and by using those sensor libraries you can get an idea about how a particular sensor is interfaced. For this, first you need to know about what kind of sensor you are using, what kind of sensor you are planning to use, or what is the specific vendor of that particular sensor, from which company it is designed, and accordingly a dedicated library you can use. The first option we always recommend is you check data sheet of your sensor. For instance, if we try to do it for one of the sensors like SDS011 sensor datasheet, if you search it like this, always do this analysis for your hardwares, and then you get it from different vendors whoever are setting up. In my case, for instance, I was using Noah fitness sensor. Noah is a company, and from there I was taking this SDS sensor. You can have this from other vendors also. So I can go to this platform, and from here I can get my uh, sensor data sheet. I can observe different elements that are they have discussed, like this you can see, and the description about the pins or its measurement abilities they have mentioned. The features of this particular sensor also they have mentioned. You can see the measurement range they have given, the temperature range that it can sustain they have given, that I called about operating range. The relative error that you can expect from this particular sensor, that is also mentioned. And these quick ideas about your sensor along with its pin description you will find over here. Similarly, the detailed data sheets, this is just a quick version of sheet I have obtained from Components 101, a popular website for the data sheets. Similarly, in many data sheets, they will also mention about the dedicated library that you can use for this particular sensor. Otherwise, you can search that within your Arduino IDE platform also. For instance, we will do first for your DHT11 sensor. That is one of the most basic sensor we have. So first you will check in your datasheet that whether your sensor works with a library or it can work without a library. If a sensor works with library, you first need to install its library, and example about how to use it in the software that you will find with the library itself. So the same thing we are going to do today for all the sensors, since all of them use library, and there will be a dedicated technique to use them. In tomorrow's session, where we will be discussing about one more case study, in that I'll be using sensors without library. So there we will be learning how we design code ourselves for sensors that do not use library. So both steps you will learn in these two case studies, using libraries and using sensors without libraries. So what I'll do here is I'll go to the library section of my Arduino IDE, and I'll start with my first sensor, that was DHT11. I'll search for this, and then I'll try to observe what libraries are available for this particular sensor. So this, you can see there is a long list of libraries. As a beginner, you sometimes get stuck that out of such a big list of libraries, which one you should choose. So in that case, what you can do is either you can take reference from the literature. They mention it sometime in literature also, that which one is recommended. Sometime you can find that information exactly in your a data sheet, that which of the library is compatible with your kind of sensor, or you can search Arduino official website. From there also you will find what are the recommended libraries for your specific type of sensor. So in my case, for instance, I have already installed this DF Robot DHT11 library, as well as I have installed this DHT sensor library. These two I have already installed because they both are compatible with my sensors, and they allow me to interface DHT11 as well as DHT22. This one especially. This works with both DHT11 and DHT22. Yesterday, I told you that there is a difference in terms of specifications for both these sensors. And however, this one is dedicated for DHT11 only. So accordingly, you can choose any of them. Once you have installed these library, like in my case, I have installed them. You can just click on the install button and then it will be installed on your system. Soon after that, it will be ready to use. So the next step for you is you can go to the file section, then go to examples, and inside this, in the custom library section, you can see here examples from custom libraries. Since I use several different types of sensors, so I can see a long list over here. When you are starting it for the first time, you will have only the dedicated libraries that you just installed. So here I'll find my list, that is your DHT11 sensor. So for that, this one I have DHT11 sensor. The basic technology for this is with DF robot that we can use. I'll click on this, and as a beginner, you will get a quick code to interface your sensor with the software here. For instance, you can see this is a pattern to add a library and its text. They will provide you the default pattern to learn parameters from your sensor itself. For instance, first we need to include the library. Then we are setting up a object for calling that library. You can also call it something like a nickname we have given to the library that we can use throughout the program. Then I'm defining a pin for connection of data line of my sensor. So the data in this case will be transferred on pin number 10 of Arduino, and accordingly the wire I'll be connecting. Then we have the setup section where I'm using serial.begin 115200. Understand this carefully. Yesterday I told you that on Arduino IDE screen we have this serial monitor that we can use to check the quick updates on sensor data. But for that, we first needed to define the baud rate of the system. And that baud rate is defined like this, serial.begin. And here I'm using 115200 as baud rate. Another commonly used baud rate is 9600. That is also compatible with your serial monitor. This basically helps you to know the speed of data transfer from the readings collected from your hardware and then displaying it on the serial monitor. Then we go to the loop section. As we discussed yesterday also, that this section is for one-time initializations or one-time task. And since sensor data will be reading multiple times, that will be like a loop-like task. So we are inserting it into while loop. And here, very first thing, we are just reading data from the DHT sensor. Then we are using serial print. This is a static print. I'm just helping you to understand the coding process. Whenever we write anything in inverted comma, it is printed as it is. The temp with colon will be printed as it is. And ahead of this, the temperature value will be printed, since we are using a temperature function from the DHT library over here. So that value will be automatically printed. And right after that, we are writing humidity with a nickname humi over here. That will be printed as it is, considering it again a static text, since this is within inverted commas. And then we are printing the value of humidity by using humidity function on the DHT library. So this is how we are organizing the sequence of code to get printing from the sensor data on the serial monitor. And then we are applying a delay of 1000. 1000 here means 1 second, because by default Arduino IDE takes 1 millisecond delay. That is the minimum delay it has by default. So when we write 1000, that turns out to be 1 second delay. So accordingly, we can increase delay and we can set up our sampling sequence for the field data. This is one of the most basic interface we have studied with DHT11 sensor, and the library type is dfrobot over here. In case if you are not using dfrobot library, if you are using other library, you can check example from that also. Like first I'll close this and I'll check example from the other DHT library. For instance, this one we have over here. Depending upon what library you are using, the code will be defined accordingly. So that is completely dependent on the library itself. For instance, in this second case, how do they use it? They first use the Adafruit library, then they use DHT library. They have also used one additional library. Then they are defining the pin number to connect. Since this particular library works with all types of DHT sensors, so here you can decide whether you are using DHT22 or DHT11 or DHT21, which one you are using. Accordingly, you can turn that on, and remaining they have in the comments. Similarly, then they have defined the type of sensor and pin of the sensor, and they assigned it to a specific variable over here. And ultimately, they are using the setup section. In this, the pattern you will see is different. They are printing so many things from the sensor itself. Then for the humidity also, different information they are getting, and they have this within the sensor library itself. Min value, max value, resolution, or sensor ID, version of the sensor, everything they are printing. So this completely depends on our requirement, what we want to see out of the results obtained from the sensor. Accordingly, we can print. And here also you can see in the loop section also they are adding so many things. So this completely depends on what type of library. dfrobot is generally one simple library that anyone can interface. Then depending upon which further extension you need in your code, you can use other libraries also. But just make sure that it is compatible with your type of sensor. You can do hidden trials also by checking different types of libraries and then see whether your sensor is being read or not. After this, the second example we had is, for instance, with SDS sensor. So for that, we can proceed here with the SDS sensor example. This one I can see, Nova SDS011 sensor. As I told you that we have used it from Nova Fitness. So I'll go to the example. Again, the same pattern. And here, as a beginner, again, you can observe what are the code sequences that can be used for this type of sensor. For instance, here they have used this form. This is a very lengthy code you will see. So as a beginner, sometimes people get confused that this is a very complicated code to run your Nova Fitness sensor. But if you change library, for example, I'll show you one more library that offers a easy way to interface this particular sensor. This is how, as a beginner, you may need to test different libraries, and once you find easy to read one and easy to understand one, accordingly you can use this one. You can see SDS011 selectable serial sensor library. I have used this one. And observe it. It allows you two different examples to use. One is hardware serial, other is software serial. Now we need to understand difference between both of these. If you remember the PPT part, I have shown you that there are two hardware units that are using UART based communication with transmit and receive lines. If anyone remembers, they can let me know which were the two devices in our hardware selection that were using UART communication. Anyone in the chat box? Two devices that we want to communicate with transmit and receive lines. ESP32 indeed, and the other one was this SDS011. So there were two devices that we need to connect on TX and RX line. But if you remember the pin diagram of Arduino, we have only one TX and RX line, dedicated line, that is on pin number 0 and 1 of your digital port. So this dedicated TX and RX line on Arduino is called hardware serial. Means it is already available on the hardware, and accordingly we can make connection. So that we call hardware serial. But since in our case we need two different sensors to be connected on the similar type of lines, so instead of just relying on the hardware serial, we may also need to use software serial. Software serial means when we can dedicate any other pin from the digital port to be used as a transmitter or receiver. Understand this very carefully, because this will be very helpful when you combine multiple sensors in your project. If there are multiple devices looking forward for similar lines like transmitter and receiver, you can dedicate any pin from the digital port to be used as a transmitter and receiver separately. For instance, in my case, the hardware serial, for example, I'll dedicate to ESP32 so that it can use that automatically. ESP8266, for example, in this case we are using. So ESP8266 can use transmit and receiver from the hardware serial. And for this SDS011, I'll dedicate other pins, like maybe pin number 10 and 11 I'll use as receiver and transmitter respectively. So accordingly, I can use the software serial code for that. And the difference in both cases you will observe here is because they are giving both examples. In your case, if you don't need the software part, maybe the hardware serial is already free, then you can check only the hardware code for this. So for instance, I'll first open the hardware serial code. And in this case, you will observe here, see this one. First, we are including the library. Then we are declaring two variables for measuring PM10 and PM2.5. And one variable is int error, that is to check status of your sensor. If there is some error prone connection or the connection is fine. So that with int error variable, we can check further. And then we are dedicating serial 1, that is the hardware serial, to your sensor, and the object name here we are declaring is my SDS. Any name you can give. They are giving it a name, my SDS. And serial 1 means on the hardware serial it will be connected automatically. Then in the setup section, one serial begin we are using for the serial monitor that we have discussed already also. And second serial begin we are using for the SDS, because now SDS also need to communicate over transmit and receive line, and that also needs a baud rate for working. Depending upon how many serial port connections you are using for this transmit and receive line, accordingly you may have to decide multiple baud rates. They can work on same baud rates also, or you can assign different baud rates also depending upon the sensor requirement. For example, in case of serial monitor, I can even assign the other baud rate that we discussed earlier, 115200. But for SDS sensor, it works only on 9600. If I try to change its baud rate, it will not give you results. So accordingly, you may first need to check specifications of the hardware, and then only you may have to decide the baud rate also. After this, we go to the loop section, and then we are using a function from the library itself, and they have a read function that focuses on the address of both the readings that we need to get from the hardware. That includes 25 P25 and P10 for dedicated for particulate matter 2.5 and particulate matter 10. And we first, depending upon the requirement of the function, we measure it first into the error. And if it finds that data is being accumulated well from that target position, we can enter inside this if condition. You can see if no error. I have used a exclamation sign over here. So this represents if no error is present, then we'll be printing the value of PM 2.5 and PM 10. Otherwise, it will just check for the next reading again, and it will display the error accordingly. That error display sequence also we can write. Although in this they have not written that, but we can easily display that by using serial print within bracket error. So this is a simple sequence you can use for hardware serial over SDS. In the similar manner, if we want to use software serial for this, for instance, in the example section, I'll find the other option that we have. Within the library, we have software serial, and we will see what changes will happen with this selection. So in this case, you may first have to declare the pins that you need to use for the dedicated connection over here. So for this, first you can see we are setting up the SDS library. Then we have one more library, that is software serial library. This is to declare additional pins from your hardware for being used as transmitter and receiver. Then the same thing, your error and sequences for your PM we are using over here. After this, we have the software serial dedicated to the pin numbers. These pin numbers we are marking here as receiver and transmitter in sequence. And the name I have given is my serial over here. So with this my serial, we are updating here, dedicating it to the my SDS. With this my SDS, whenever we are making software serial connection, it will automatically communicate through line number 10 and 11, and that will be connected on the other side with the respective pins of your sensor. Further, your setup section is same as previous. We just have to dedicate both baud rates over here. Then we have the loop section. This is also the same. Just this section we have added up as additional portion over here to dedicate our mentioned pins over here. So this is how you can interface any new sensor from the UART category to your hardware. Similarly, the next one, we had one sensor with I2C interface. So for that, if we try to observe it further, we have here CCS811 sensor, this one, SparkFun. Now you will observe this again, very important. This CCS811 sensor you will find either from Adafruit or from SparkFun as well. Adafruit and SparkFun are two popular vendors that design this sensor. So here what we can say, depending upon whether you have, again, whether you are measuring it with Adafruit based sensor or SparkFun, that will be written on the sensor itself, that which vendor you are getting it from. Accordingly, you can choose the library. In my case, I have taken it from the SparkFun, so accordingly the library I have selected. And from this, again, you can see there are multiple examples, because this sensor requires you to have different types of compensations also for measurement. Sometimes you may also need like sensitivity adjustments on this sensor. This comes like a very important part again. When we are talking about some gas sensors, you may always need a different set of calibration techniques or sensitivity adjustment techniques. That is essential for your gas sensors. Why we need sensitivity adjustment or calibration adjustment over here? The reason for that is, for instance, whenever you are getting a gas sensor from a factory, it is not always essential that it will be factory calibrated. Sometimes we get sensors in the factory calibrated form that can be deployed directly in the field environment. Sometimes with the sensor from the factory, you will get procedure for its calibration. That calibration you have to do before you deploy it in the field environment, and for that they provide you procedure in advance. Like they have given different codes over here, how you can mark different compensation, how you can adjust different sensitivity levels that they provide in advance. So that code, dedicated code, you can follow with a specific hardware arrangement, and accordingly you can follow it further for the adjustment of your sensor readings. In this particular sensor, you need reading for compensation of temperature variables. For instance, this sensor get influenced by variation in temperature or humidity in the surrounding environment. So this requires a compensation pattern, and that they have provided over here. Either you can buy a CCS 811 sensor with inbuilt temperature humidity sensor, that is also available in the market. Like they integrate a BME 280 temperature humidity sensor within the same module. So in that case, the compensation will be automatically provided with a dedicated code. But in our case, we have purchased a sensor that doesn't have on-chip temperature humidity compensation. But because in our case, we were using a DHT11 sensor already in the project, so we could use temperature and humidity compensation from there itself. It means we need to integrate our code in such a manner that it should first take a temperature humidity compensation and then measure reading from the surrounding environment by considering those thermal comfort parameters. So these are some adjustments you have to make for the accuracy of your measurement sometime. And here, for instance, the basic readings, if you want to see that how we measure basic readings from this CCS 811 sensor, that we can visualize with its example. For instance, first of all, you need the library of your sensor, and along with this, there is one more library that we call wire library. Now, this is one more library you need to understand. Whenever we are making a I2C based interface, I2C communication, that is a bus type interface basically. Consider it something like I2C is basically a bus type communication. You can say like you are taking a bus and you have to reach a certain destination. So to the conductor, you first tell that you have to drop me at this particular destination, depending upon the route of that bus. So here also same thing is happening. We need to mention a address of the sensor from where the microcontroller has to pick data set. That address we have to mention in advance. So that address is listed over here. You can see address of CCS 811 is 0x5B. But what if you don't know this address? If the hardware that you have purchased, you are not aware about its address in case, then we can take help from wire library separately also. This wire library will help you to scan the address of the hardware connected to your Arduino, and it will help you know that which specific I2C address you can use to pick data from this particular sensor. This is one option. Second option is you can always check the specification provided by the vendor on the datasheet, and there they will mention all the I2C addresses that are compatible with your type of hardware. So in our case, like for instance, the manufacturers have given these two addresses, 0x5B and 0x5A. Any of these may work. So we may have to test which one is working with our hardware, and then accordingly we have to incorporate it in the design process. And wire library will always help us to link to this particular address. So this is how we set up different things into the system. Then we are dedicating that address to the sensor, and we are calling it my sensor. You can give any name to this. Similarly, in the void setup section now, we are using serial begin. We have already discussed this. This is just a static print that you will observe. Then wire begin also we need to use. This is to initialize I2C hardware, and it doesn't require any kind of baud rate. So empty initialization you can do here. Then this particular sensor requires you to check first whether the wiring is correct or not. So for that, they have a dedicated operation, my sensor dot begin. Note that although you can use it only this section also, that will be also fine. But in that case, you will not be able to see whether your sensor is into some error or it is working fine. So if you need to see that information clearly, you can use this entire if condition. So accordingly, it will work further. Then we have the loop section. In the loop section further, first we are just checking the data available from the sensor. Then there are some dedicated algorithms designed within this library that help you to read most accurate results from the sensor depending upon if any compensation is provided. So based on compensation also, I'll show you one example with the entire code that we'll be discussing further. Then we are just printing that CO2 and the VOC outcomes. TVOC represents here total VOC, all the components included within the VOC that will be displayed. And the functions again we are using from the library to get those gas reading. So this is how the entire code from the library you can understand again, and you can modify it as per your requirements further. One more sensor that we had in the list, for that also you will find a dedicated library over here. And as I told you that this particular sensor can be used for measuring like a very huge range of parameters. So it completely depends how many of them you want to access from there. And you can see again with this library, you can find the calibrate code also, because this sensor also requires you to do field calibration before final deployment. So that calibration code you can use from here. And then read gases also we can use as a sample. If I just check this one, you will see they are able to read multiple types of gases from this hardware easily. For instance, first they are including the sensor library. Then they have declared an object for this. A bool they have declared as an additional object to just check whether your sensor is connected or not. You can see it is being used here with sensor begin. Last time also we have seen this. This one we already know in the setup section. For your serial connection we can use it. And then they are testing whether your sensor is following the hardware connection properly or not. Definitely this is an optional section. If you want to ensure every time this recheck, you can add this in your code, otherwise you can avoid this. Then in the loop section, you can see they are just using the inbuilt functions to measure each one of these parameters, and accordingly they are setting up the connections. This is one way to measure this particular sensor. There is one more way to do this. This sensor also works well on the analog channel, as I have shown you in the image earlier. So on the analog channel, you can connect it directly with A0 and A1 or A2, A3, any of the pins, and you can read them directly from your code to run it independently on the system. So that is also possible. Either you can use functions from the library, or you can use directly analog read functions that are available within Arduino IDE by default. So this I have shown you all parts of the sensor codes that you need for the interface. And now let us just observe how the complete set of codes for this particular application will be designed. I'll show you one already designed code from here because we cannot design it from the scratch in limited time available. So here we have, depending upon the hardware connections that I have shown you on the PPT already, you can see the connection descriptions I have given first, that these will be the pins connected on the hardware side. For each one of the sensors, you can see the descriptions I have provided here. And then further, I have segregated this code into different sections. And you can see the libraries are included first. This section is for all the libraries. All these libraries we have already discussed. This is one additional library, STD library. This is basically when you are expanding your codes with further different types of macros, functions, or variety of header files further. Then this std library we can use for getting enhanced support for the smooth operation of your program. So this is basically a support library, standard library we have for the enhanced support to different types of functions within your this code. Since I'll be using multiple declarations in my code, so I have added this support library for smooth functionality of my code. Further, the pins I have dedicated for my SDS sensor 10 and 11 respectively as RX and TX. Then we have dedicated the object for this with my serial, since I'm using hardware software serial, so accordingly my serial I have dedicated. In case if I'll be using hardware serial, I can use serial 1 directly, that we have discussed. Then I have decided pin number for my DHT sensor and the type of DHT sensor. This selection completely depends on type of library you are using. If you are using DF robot library, you need not to declare type of sensor because that works only with DHT11. Then we are just accommodating both of them into DHT object. Further, we have decided the address for CCS811 sensor, and again we are dedicating it to the object of CCS811 library. So these are the initial declarations for setting up all your libraries with respect to the dedicated pins on the microcontroller. Moving forward, we have declared all different types of variables that we are planning to measure. Definitely, you can declare variables of your choice. There is no restriction that only these names you may have to use. You can use any names, and the same you have to use throughout your code. One error variable also have used. This will be used for your SDS011 sensor, as we have seen an example. So for the testing whether it is working fine or not, I can use this code further. Then further, I'm using this Wi-Fi section because I need to send my data to the cloud also. So these are additional details I have over here for interfacing with your ESP8266 Wi-Fi gateway. In order to access your internet, I first need to provide it SSID and password. So the details I'm mentioning over here. Then since I'm using ThinkSpeak as my cloud interface over here, so the IP address of ThinkSpeak I have to mention, and I have saved it within the IP variable. This is currently my cloud interface address for ThinkSpeak. This is a standard one. All of you need to use the same if you are working on ThinkSpeak platform. Then we have the channel key for your ThinkSpeak account. For instance, depending upon how many channels you have, what account you are using, from there you will get this API key. And it is important to mention here that this is a secret key. If you disclose this key to anyone, it is better to change it immediately. Otherwise, other people can access data from your channel, or they can send data to your channel. So this is basically a secure key that you may have to use, and where you will find it on your channel. For instance, if I open up ThinkSpeak platform, since I have already logged in here, and I'll go to a specific channel that I'm using right now, and here you will find API keys. You will go to this API key section, and this is the thing I'm using right now, this API key, a secret key. And once, in case if you have to share it with anyone, you can share it, and later on you can generate a new API key, and you can just get rid of the previous one to ensure that your account is secure or no one else is able to send data to your channel. They have both read and write API key. When you have to write on the channel, you will use write API key. When you have to export your data further for any kind of data analysis or prediction, you can use read API key accordingly. So getting back to your code, further in the setup section, first of all, I have used serial begin with 115200. Then I have my serial begin, this one, as I already told you, for SDS011 sensor that works on the dedicated 9600 baud rate. So for that I have used it. This one I can mention for the serial monitor. Then for the Wi-Fi setup, this section ESP 8266 setup I'm using. Yesterday also I told you that we have some 80 commands to communicate with variety of gateways. 80 commands work with GSM gateway also, with Bluetooth gateway also, and with Wi-Fi gateway as well. So here we are talking about the Wi-Fi gateway, and within it we have, first we can send a 80 command from the microcontroller to the ESP board, then a delay of 5000, and I'll wait for a OK response from the ESP to ensure that it is ready to communicate. As soon as I receive a OK from ESP, I'll connect to Wi-Fi. And in order to connect to Wi-Fi, again, I have created a different subroutine in my program that is mentioned on the bottom. Here, I have this. So I'll be using this. I'll be simply calling that subroutine in this particular section right here to connect with the Wi-Fi. I'll show that subroutine further. Then a simple print sequence for initializing everything. DHT begin, because DHT sensor doesn't require any kind of baud rate, but the library requires to initialize sensor. So DHT.begin I'm using. In case of if you are using DF robot, that doesn't require initialization, so then you can leave this begin part. But in this library that I'm using right now, this is requiring begin, so accordingly I have inserted it here. Similarly, begin for the wire library that I need for CCS 811 sensor. Then this section we have seen in the example of your CCS module. This is basically to check if your sensor is connected well, or if there is any wiring error or any other breakage error. So that will be mentioned with the return code, and accordingly you can recheck your sensor, or if any fault is there, you can just repair that. Further, we go to the loop section, and here I'm just checking if there is no error. Means if all the initializations above have done well and there is no error in our system, then we can proceed with the start level further. And that start level will take you to the first line of your code automatically. That includes serial.println. This is just an empty line we are printing. I'm starting first with the multi-gas sensor. You can observe here, I'm just measuring. This is the analog channel read technique. Since I told you that this sensor we can use with the library and without library also, so here I have given you one example without library. I'm connecting it on the analog pins as defined in my hardware design. So I'll be using directly analog read from A0 and A1 pin. And within this, you can see I'm just storing my values on these two variables that I have declared on the top as global variables. Remember that whenever we declare variables before setup section like here, they are called as global variables, and the values stored in them can be used throughout the program. If you declare any variable within any specific loop section or any specific area that is used on the small subroutine, then it will become a local variable and you cannot access that variable outside that section. So here we are using the global variable so that I can access them anywhere in the program. Now I'm printing all these values along with the unit of the gases. Generally we measure them in ppm or ppm, so called pbb or ppm. So here I'm using ppm since my sensors measure in this form, so that unit I'm displaying over here. Then moving further to DHT11, based on what functions are available in your library. I have in this library read temperature and read humidity functions available. So the same I'm storing in the dedicated variables and then I'm displaying them. There is one more addition you will observe, comma 2. The variable name and then comma 2. That clearly means how many numbers you want to display after decimal. If you want to control that, you can use this dedicated number. Otherwise, whatever is the ability of your sensor, accordingly that number will be displayed after decimal. So these changes you can make as per your requirement. Then unit, and same goes for the temperature sensor. This is an empty line just to add some clarity to your outcomes. And then a delay of 2000. Here also I have added a delay of 2000 so that a 2-second delay it takes to move to the next sensor. Then I have added one more section, that is your SDS011. And this is exactly same program that you have seen in the example also. Just one thing I have added here is the unit of measurement. For both the measurements, I have done that. And this is how we are measuring the third sensor. Then we come to the CCS811 sensor, for which I told you that we need environmental variables for the compensation, so that it can measure your gases more accurately. So what I have done is, within the library, I have a function available for setting up environmental data, where I'm passing the humidity and temperature values obtained from here. You can see the same variables I'm using below. I'm taking first measurement from temperature humidity sensor, and that I'm using for environmental compensation with CCS 811 library. And once environmental data is applied, then I'm reading the values from the sensor, and I'll be dumping the first reading always. Whenever I turn on the system, I'll always dump the first reading. Reason being, because it is assumed that during this sensitivity procedure or this calibration procedure with the environmental data, it doesn't compensate well with the first reading. Rather, it takes some time and then it provides accurate reading. So accordingly, the first reading I'm dumping, and after that, whenever the next data is available, I'm reading that again, and I'm storing that in specific variables, and ultimately I'm displaying them one by one with their respective units and values. Again, a delay of 2000, and this is enough for all the sensors that I have connected in my system. So up to this, I have just measured everything from the sensors, and I have displayed that on the serial monitor. But my requirement in this particular study was to get data set on the cloud platform, for which I have ThinkSpeak. And for this, the Wi-Fi credentials and the IP address, etc., I have already provided. So after this, I'm using another subroutine here, update temporary data to cloud platform. So whatever data it is getting from the sensors, it will be updated to the cloud platform by using this subroutine. And this I have created here. There is a delay also. The retransmission sequence also have created. This was available on the top also, so that is closed here accordingly. A delay I have added for the next reading, depending upon how much sampling time you want to give to your hardware. Accordingly, you can update this delay. Now we come to the first subroutine, that is to update values on the ThinkSpeak platform. So for this, we create a specific packet sequence, and that packet sequence also use AT commands. AT plus CIP start, it will start your TCP connection for transmission of data over this IP address. This IP we have declared on the top with the IP address of ThinkSpeak platform. Then we have defined the port number 80. Port number 80 is dedicated for the ThinkSpeak platform. You can communicate over port 80 on that as an external user. And then we are just printing this packet up to this point. And the IP address, everything will be printed up to this. Then a short delay of 2 seconds I'm updating. And in case if any error, it should return. If there is no error, then it should proceed ahead with the message sequence. You can observe here. And what is that message sequence now? In every field of my channel, I'll be updating the parameters one by one. You can observe here. First temperature, then humidity, then next field 3 p.m. 2.5, then PM 10 I'm updating. Then here I'm updating, for instance, CO. Then I have NO2. In this section, I have CO2, and here I have VOC in different 8 fields of my ThinkSpeak platform. And the same sequence you have to follow here on the ThinkSpeak channel. In the channel settings, observe this very carefully. These are my field sequences. The same I have to use in the code. Field 1 I have dedicated for temperature, field 2 for humidity, and then so on. I have dedicated all the fields. And you always have to mark this section as this tick mark. Then only these fields will be turned on. Otherwise, they will stay off and the graph for them will not be displayed. So this is how the sequence for data transfer we have created over here for all the fields. This is for field 5, for 6, for field 7, and then for field 8 of that dedicated channel. Since we are using 8 parameters only, so one channel is enough for us. Then we are just closing the sequence. CIP send we are using here. This is just to calculate the length of packet. That packet is containing your IP address, your protocol information, your field IDs, and your values on the field. So that packet length we are calculating here so that it can be mentioned during the transfer protocols by the system inside. And ultimately, we are closing the sequence. If there is any error, that will be displayed. Otherwise, we'll proceed further. And then comes the next Boolean sequence or the function, that subroutine that we have created, that is connect Wi-Fi. This I have shown you on the top. In the setup section, we have called this connect Wi-Fi subroutine. And this is a Boolean subroutine, means a true and false only it will give. If Wi-Fi connected, it will return a true on the top. If not connected, it will return a false on the top. And accordingly, the action will be taken by the system. And inside this again, 80 plus CW mode 1, because your ESP8266 works on 3 different mode of communication. One is access point mode, other is station mode, and third one is the combination of access point and station mode. In our case, we want to use it as station mode, so we are using it in mode 1. Otherwise, you can use mode 0 and mode 2 as per the requirement. Then we are using 80 plus CWJAP. This is to set up your Wi-Fi connection over dedicated SSID and password that we have declared on the top. So this command will do the Wi-Fi connectivity with the dedicated credentials. And then we are just displaying them. If it is returning true, accordingly we are sending it on the setup section. Otherwise false, accordingly will be informed in the setup section. That you, if remember, it is mentioned right here. Connect Wi-Fi subroutine, it is mentioned right here. So whenever we are getting a true response, accordingly it will set up the Wi-Fi connection and it will proceed further with the hardware data collection, and it will be sent to the Wi-Fi. So this is your software setup for designing IAQ monitoring system right here. Furthermore, now let us discuss the hardware design. One by one, I'll set up all the hardware units for you, and then we will observe with this particular code only, we will transfer it on the hardware, and then we will try to see readings on this channel right here. Currently, you can see what it says. It says last entry was made 4 hours ago. When I was just testing the hardware, last entry was made 4 hours ago, and these are the entries you can see. Because this particular channel is just for the testing purpose, so you will not see very frequent data. So these are some data points we can see for all the observations. Now let us see if we get the recent data over here. For this, we will first connect the hardware based on this description that we have given. Either we can follow it from the hardware here, or we can follow it from the pin descriptions that I have highlighted as a comment in my code itself. So anywhere you can follow, and accordingly we can set up things. So for instance, I'll just open up the hardware section for you. I'll turn on the camera for that, and one by one we'll make all the connections. Just give me a second. I'm setting up the hardware. Okay, so the screen is ready for all of you, and here only I'll be putting up all the hardware units. The very first thing we need is the Arduino. This one we have discussed yesterday also. And along with this, we need a breadboard. Reason for using breadboard is that this time we need extensions for the hardware connection, because we need multiple 5 volt, multiple 3.3 volt, and multiple grounds. So that extensions I'll be creating on the breadboard over here. Then one by one, we will be connecting these sensors. This is the first sensor I have, CCS811. It is written on the top of this sensor, and the pins, the wires I have already connected here for the relevant pins that I'll be using. And based on the hardware description, we'll be connecting them. Similarly, we have this DHT11 sensor for measuring your temperature and humidity, and the three pins we have on this, and accordingly I have connected them with VCC, ground, and data. I tried using red or orange wires for my VCC connection and black or gray wires for my ground connections, whatever is available as a color code for me. And accordingly, I'll be updating that on the breadboard also. Similarly, I have this sensor as my dust sensor that we have seen already. Also, we need one more wire to be connected here for the transmitter. So we have transmitter, receiver, ground, and then VCC. Accordingly, the wires I have connected on this sensor as well. And then one more thing we have is your multi-gas sensor. So for this one, again, 4 wires I have connected, and depending upon what measurements we want to do, the pin sequences for CO and NO2 I have used, and the middle one I have kept F1 for NH3, since I'm not measuring that right now. So these are all my hardware units I have just shown you. And other than this, we may need this ESP. Today I'm using ESP. In tomorrow's case study, I'll be using ESP32 Vroom. Today I'm using ESP8266, the mini Wi-Fi module. So accordingly, we'll learn other things also tomorrow. You will at least come to know that how these different hardwares you can set up in your any kind of applications further. So first we are learning this version. So I'm just removing all of them, and I'll be connecting them one by one. The same you can follow whenever you are designing any kind of hardware at your end. The very first thing that we need to do here is setting up the common connections for the breadboard. And for that, whenever you do hardware connections, we always recommend setting up ground connections first. I'm using these 3 wires. The black I'm using for ground, orange for 3.3 volt right now, and this red for my 5 volt I'm using. And I'm first going to connect ground. Whenever you connect any hardware on your system, first secure the ground point. That is most essential. So here I have on the power port, I have the ground connection, and I'm using it, for instance, here on the breadboard. I hope you all know how we use breadboard. We have these terminals are horizontally connected, the outer ones, and the inner ones, these are vertically connected. These ones are also vertically connected. And for the horizontal connection also, we have these first 5, they are connected together, and similarly the last 5 are also connected together. So if you need to use the entire channel altogether, you may have to add some jumpers here first, and then you can use the entire channel altogether. Currently we don't need so many connections, so I'll be using one section from here, one of these sections for my ground. Other section I can use for VCC, or one more section from here I can use for 3.3 volt also. So that is based on our convenience, we can update. So the second one I'm picking up is your 5 volt. Right from here in the power section, I have 5 volts, so I'm putting it right here. And then we need a 3.3 volt that I'll be updating, for instance, in this portion. Based on your convenience, you can choose any sections. Now I'm using the very first sensor, that will be my DHT sensor. I'm taking up the first wire. I'll be using ground for the safety purpose. I'm inserting it right here. Then the VCC connection I'm using in the VCC section, and then this data point as defined in your hardware or your software. If you remember, we have used this one on pin number 7 of your digital port. So accordingly, I have connected it on the digital port pin number 7. After this, I'll be connecting this SDS sensor, And as we discussed earlier, it requires UART based communication through transmit and receive lines. So the very first thing I'll do is I'll pick up its ground connection, the ground wire I'm taking up, and I'll be inserting it in the ground section over here. Then I have this VCC. It works on 5 volts. So accordingly, the 5 volt I'm inserting here. Then we have these two. I'm connecting all wires one by one, and I'm describing each one of them. Since I'm using open wiring right now, within few seconds, you will see there will be a mess of wires. So try to understand every connection right from now. Otherwise, later on, you will not be able to observe any of the connections due to the open wiring over here. So I'll just keep it right here, and I'll be connecting these two wires. The green one is the transmitter on my sensor, and this brown one is the receiver on my sensor. Accordingly, I'll be using them alternatively on the pins that are software serial declared. So in my software, if you remember, I have declared pin number 10 and 11 to be used as receiver and transmitter respectively. So the transmitter from my SDS, the green one, I'll use on the receiver pin, that is pin number 10. And similarly, the receiver from my sensor, sorry, this one, green one is my transmitter. So that I'll be using on the receiver, pin number 10. And brown one I'll be using on pin number 11 as transmitter on the other side. So the opposite connection we have framed over here. Similarly, I have this CCS sensor. First, I'll be connecting its ground terminal, that I'll be updating right here. And then I have 3.3 volt. This orange wire I'll be taking to the 3.3 volt section on the other side of my breadboard. After this, we have SDA and SCL pins. So the SCL, this green one, I'll take to the SCL, that is the last pin of my digital port. And the second last is SDA that I can use from here. Otherwise, you can use it on the analog port also. The last one pins from there as well will work. After this, I have this multiple gas sensor. First, I'll connect its ground again. So this second wire, gray one, is my ground. And I'll be inserting it in the ground section right here. Then I have this VCC. It works on 5 volts. Accordingly, in the VCC section, I'm connecting it. After this, we have the A0 and A1 pin that I have declared in my software. So the first one, this purple one, is my A0 pin for CO, and the other one is on A1 accordingly for measuring NO2. So all the sensors now I have connected, you can observe here. So before I connect my Wi-Fi unit, let us see if all the sensors are working fine with the code or not. So I'll be connecting this wire. Just give me a second. I'll be taking it out. So you can observe I'm just connecting it on the USB terminal of my, just give. Okay, so getting back to it, since I was having limited USB on that side, so I just changed the terminal, and now I can connect my hardware over here. And you can observe that this has turned on now, and if some wires, due to the change in the sequence, if I have removed something, I'll be connecting it back. We just need to make sure that all your wires are precisely connected and none of them are having any loose connection, because otherwise it will create trouble in your measurement itself. So this one I have connected, and then VCC also I have connected. This one also I need to secure again. So now I have settled up everything, and you can see some LEDs are turning on the system. And side by side, I'll be opening the software side of your the code that we have already designed. So I hope we can see it side by side. I'll be using other layout for easy visibility. Okay, hopefully now you can see both of the windows side by side. So I'll be opening up this one. So this code basically we need to check on the hardware. So what I'll do is I'll first choose Arduino Uno and pin number 8 from here. I'll just upload it on my software. Uh, it says done compiling and then it is uploading. Within few seconds it will complete upload also. Now I can open up serial monitor, and here we can observe the readings. You can see all these things we were trying to write, and readings from the sensors we can observe. Maybe some wire from this sensor is taken out. Let me just connect this wire back. I have connected it again and I'll just rerun. Now you can see temperature and humidity readings are also arriving, and I have just refreshed all the readings, and accordingly all sensors are updating their values over here on your screen. You can observe from the premises where I'm sitting, it is providing this information. These are the gas levels or dust levels right now, temperature and humidity levels, as well as CO2 and TVOC levels. So this is a quick observation with the hardware itself. Now we want to send data to the cloud platform. Right now you can see that it doesn't show anywhere the information about the Wi-Fi credentials. They are not connected, although it is framing the packet, but it is not sending data right now because that packet sequence on the field level it is not showing, because Wi-Fi is not connected, that is why. And ESP is also not connected. So in order to do that, what I'll consider here, I'll simply connect my Wi-Fi module first of all. This module, all the pins of this, and again a safety decision we have to make here. We need to take out the power cable first. Whenever you do any troubleshooting or any wiring update, always take out the power cable so that your sensor stays safe, otherwise they will malfunction. And then first of all I'll connect the ground terminal of my this ESP board, and I'll be using a separate ground for safety reasons on this particular. So I'm taking it from the digital section of my Arduino. Then I'll be taking up the VCC. I'm using this orange and red wire. Since this particular gateway works on 3.3 volts, accordingly I'll be taking this 3.3 volt section from the hardware. The remaining wires, one is receiver and other is transmitter. And I told you that this ESP will be using on the hardware serial. So the receiver I'll be using on the transmitter right here, and the transmitter I'll be using on the receiver right here. And as soon as I connect my wires again, you will observe a red light on this sensor, and as soon as it connects to the Wi-Fi. So for that, since I'm using Wi-Fi from my mobile phone, I'll be turning that on, and it should display the device connection. For instance, right now, I'll just refresh this connection, and soon after that, it should display the connection, and there should be some blue light also blinking over here. And we also need to ensure that all the wires are well connected for this. I'll take just a moment for setting up the Wi-Fi connection, because sometimes the sensors take little bit of time to set up the connection on the Wi-Fi side. Okay, so let me just check it once again. The hardware connections, if any wire is loose, I may need to repair that. I'm uploading it once again. While uploading, we always need to take out the receiver and transmitter wires. Otherwise, they will interfere with your communication on the channel. So we always take out transmitter and receiver wires for this. Probably due to some signal issues, I'm not able to connect to the Wi-Fi right now. I'm just trying it once again. Okay, I have just replaced the ground connection and now I can see, you can observe here, I can see here ESP32 connected on my phone. And now I can refresh this connection on the reset button also. And based on this on the screen, you can see this key update. This shows that your data is being transferred to the Wi-Fi platform. So this you can see it is making connection CM mode 1 and then the credentials of the Wi-Fi, and accordingly after getting all the sensor data depending upon how much delay we have given to the system, you can observe it is sending data, this field information we were looking forward to. You can observe this is my field, this is my API key, then field 1 is receiving this data, then field 2 is receiving this data, then field 3 and so on. And the same we can observe on your ThinkSpeak platform. You can observe less than a minute ago. Earlier it was like 4 hours ago, but now we are getting this data less than a minute ago. And we can even observe this right here. These are the recent readings you can observe. uh, for these, the timing you can see here 17.38, that is your 24 hours clock, it is representing. So 5:38 basically the last reading it has obtained, and accordingly based on the delay, the remaining readings also it will show. It is updating on all these, like humidity value it has also updated, similarly PM10 value also, the recent one we can find out from here. This one is recent exact value as well as your timing for the field update. So in this manner, you will find all the field updates from the sensor data. And later on, when you need to get this CSV file, you can click on data import export, and then you can choose the timing from the site wherever you are making the measurement. For example, for India, they have 4 different time zones. Like for instance, I can pick up New Delhi from here, and then we can download. Although this particular file doesn't have a continuous data, so we will just see some random feeds over here, but still the data we can visualize that it is gathering for all the field variables. So this data I have just instantly loaded, and you can see because I have used it on and off. So different variables, you can find the values that sensors are reading from here. From year 2019 onwards, I'm using this particular channel. So all those filled variables, it has just downloaded. The intermediate ranges, like for some time all the sensors were active. For those areas also, the readings I can see over here. Similarly, depending upon how many parameters you are updating, Excel sheet will be prepared that you can use later on for data analysis. So I'll just close this sample feed that we have received from the channel here. And otherwise, you can just visualize these. It is updating continuously. About a minute ago, again, it has updated. And you will see that right here. This, it has updated. Then the next sample, it has updated. The delays we can change based on this. And the readings we are getting from here. In this way, you can connect any number of sensors into your circuit, and you can update them on the software by using different libraries or their specifications based on their hardware connections. And ultimately, you will be able to gather data on the cloud. And the benefit of using this ThingSpeak platform for this purpose is this is available as a free of cost solution for up to 4 channels. So you need not to pay anything, and for any number of years you can keep on using it. Like you can see in my case, I'm using these channels since 2018-19, so it is working fine since then, and I'm measuring different types of variables on them time to time. I have used on them on several sites. So this makes a good solution for any beginner who want to store data online. So currently